Hello, everybody. Welcome to this little seminar. My name is Marcus Clark. I'm one of the instructors with Training Camp. Been doing it with them at least for about 8 years or so. Teaching the Sec Plus being one of the more common classes that we tend to teach. The seminar that we're going to be doing today is going to be a small little excerpt from that Sec Plus, primarily, as I'm sure you already know, the section that's labeled architecture and design, which does cover a lot of different bases. Architecture and design covering everything from basic network utilities, placement of devices, how these devices generally function together in order to form a network, and the benefits of doing that, well, frankly, the right way. So, might as well might as well get started on all of that. So again, we're here for the next 2 hours or so, give or take. So, network and cloud. The other thing that this section this section that this section does cover a little bit is an introduction to cloud terms. And the Sec Plus doesn't get very heavy into it. The Sec Plus primarily just starts touching on them. Like, this is what it means to have a cloud environment. What makes a cloud architecture, a cloud system different from your typical one when everything is co-located in the same place, in the same general area. Right, before I get started in this in earnest, let me make sure the chat window is up. And yeah, if and at any point in time, any questions or anything like that, I suppose that if any does come up, feel free to use the chat window to do that. But otherwise, yeah, I'm just gonna go ahead and get going. Right. So, starting with just the basics, right? So, architecture and infrastructure concepts covering generally what I was saying, largely about placement, what kinds of devices are responsible for what, and how that affects where they go, how they do what they do, and what greater effect they have over the network as a whole. Devices such as switches and routers, which have the general job of making sure traffic gets to where it needs to get to. So the actual addressing and forwarding of traffic is a big thing in terms of architectural design and the devices that do that job, as well as going down to the bottom, workflows. Devices exist within greater infrastructures to sort of organize traffic, right? Because a lot of the different ways that you can think about, describe, and talk about network traffic, different data going from one place to another, is the same way that you would highway traffic, car traffic. Right? If you were to have everyone in a busy area, a major city like Philadelphia, New York, you name it, all using the same highway to get everywhere all the time, you have jams, you have slowdowns, you have congestion, you have collisions. Network traffic works very much the same way. So good architecture isn't just making sure that we have bare minimum devices like routers and switches to get us from A to B to make sure we can actually get there, on ramps and off ramps, if you were, but also making sure that we have logical ways of distributing workflow, making sure that traffic has multiple ways of getting to where they need to, and making sure that traffic only needs to go where it needs to go. So organization of traffic is also a pretty big thing, a very big thing when it comes to network architecture, given that, especially if you're thinking about the Sec Plus as it is, Sec Plus is very focused towards enterprise infrastructures. What that means is the types of networks that are large scale, that are servicing entire companies, organizations, as opposed to a small network, a home network, or a small office. Enterprise networks have a lot of what goes on when we say and use the word enterprise. The emphasis is large scale. The emphasis is distribution, is hundreds of computers, hundreds of people. So this idea of meaningful and efficient, the word we're fishing for, efficient workflow is very important, right? When you have that scale, that size. So something that, at the very least in the context of the Sec Plus, that is just baseline and minimally needed to understand putting together an architecture, at least at its base. Not necessarily the more advanced concepts like how workflows are going to be organized, but just making sure a network works is everyone's good friend, the OSI model. The OSI model is a general description, is an outline of how network traffic, data, as well as devices and things we call protocols need to work together in order to make sure that traffic can get from point A to point B. And not only just that, but also make sure that the different things that we're communicating between, the different devices, the different applications, the different processes, can actually understand each other. Because one thing notable about the OSI model is devices that exist on distinct layers like 3 and 2 and so forth and so on, they don't necessarily understand protocols from specifically higher layers, like focusing on 2 and 3 specifically. If we're talking about the Sec Plus perspective, layers 3, 4, and 2 are the ones that this test primarily focuses on with it most emphasis, and a little bit of 7. But anyway, layer 2 is where we start our first addressing device, the first device that's really capable of making sure that traffic doesn't just go on the network, but goes to a specific place that is addressing, that is our switch. Standard network switch's job is forwarding of traffic based on a certain kind of address. And this is actually what changes from layer to layer of the OSI model is layer 3, for example, your router, it also forwards traffic. It also makes sure that traffic can get from point A to point B, but using a different type of address. Similar functionality, similar function wise, right? This address tells me where this traffic needs to go. This address represents a machine, but for different use and in different contexts, right? Your layer 2 address, your MAC address, MAC, your MAC address is the address that the switch uses, also called your burned in address, your physical address. This is the address that the switch recognizes as a format. That's also another important factor because in layer 3, we use IP addresses. Always the easier one to remember because layer 3 IP is a nice easy rhyme. IP addresses being at a higher layer of your OSI model, lower layer devices don't inherently recognize them. It's a different format, it's a different structure. Switches don't know what IPs are, but your device and the programs you use, like your browsers and so forth and so on, inherently use these IPs. Everyone needs to use a switch. Everyone is using IP addresses. This is where protocols come in to translate. Because naturally, your switch being a layer 2 device, not understanding a layer 3 address, because that's what your router needs to use to get to the internet ultimately uses IPs. Protocols, they have a lot of different jobs. The job of a protocol primarily, I usually put in a couple of different thematic camps. One, a common job of a protocol is a translator, right? The protocol responsible in this scenario we're talking about is called ARP, ARP. ARP's job is to make sure that your switch, the lower level device, actually can use it, not fully understand. It doesn't fully internalize it, but the switch knows that this IP address, this number, is associated with a MAC address that the switch does know, right? ARP is what allows your switch to map these associations. This is then stored in a local data location in your switch called a cache. Your ARP table is what it's called. So every time, let's say the router says that Marcus's machine has this IP, the switch just looks at ARP. ARP says that IP number, that number somebody's giving you is this MAC address. It knows who to forward it to accordingly, and vice versa, because the switch will only ever use the MAC. So, getting a little bit into each of these. Now, CompTIA Sec Plus never has, at least so far, doesn't really get into the nitty gritty of switching and routing protocols because within switches and routers, there are additional protocols that have other jobs. The main one, in terms of just establishing a functioning network, is going to be primarily ARP. The other protocols that are associated with these two devices, these two layers, are going to be about mapping, not just making sure making sure your device knows what an address is, but many of the other protocols, their primary thing is making sure these devices understand where things are in the network, not just the address someone's using, right? There's a difference between this number represents Marcus's machine versus this is how far away Marcus's device is. This is how many jumps I need to take to get to Marcus's device, right? Routers do a lot of this. Routing protocols do a lot of this where they actually measure distance because more advanced infrastructure, more advanced architectural protocols and devices can actually start figuring out what the most efficient path traffic should take is. So another, again, analogy would be like the thing Google Maps does. When Google Maps is routing you somewhere and then traffic happens, and then it tries to redirect you on a more efficient route based on the delay that Google detected. There are protocols in your network that function very similarly, right? As well as a couple of other things. But again, the Sec Plus is pretty surface level with it. But that's the farther depths you would go into if you were to be taking, more of a more network orientated, more network orientated certification like a Cisco class or something of that nature. But anyway, topology generally just refers to the layout of your network. Physical topology being the literal physical placement of devices. Logical always means non-physical. Usually when you see something called a logical map, it's referring to more of a relational map, like the switch is connected to the router is connected to the internet, not actually representing physicality. Right? Well, leave it at that. So on-premise networks, on-premise generally just that's entirely just meaning all of these devices and these systems are located at the primary office location or building, right? This is a relatively self-explanatory point slash term, but the difference between how architectural design changes for any and all things on premise versus any and all things that are remote and eventually when we get to cloud, that's a big focus of emphasis in at least this small little section is how does the basics of networking and communication change when we have to do things outside of our own local network? Essentially, once we start reaching beyond our router, how do things get affected by longer distance when we need to go across the internet, so forth and so on? So, a hierarchies is a term used to describe of the way a lot of different information security, but also just networking concepts are built. But the idea is, if you think of a family tree, shaped shaped structure. But instead of two people at the top, you have a single thing, a single entity, a single device, right? This single entity, this one thing at the very top of the hierarchy is what validates, it's what verifies, it's what allows essentially any kind of transaction function thing that happens underneath it. So anything that branches from what we call a root in a hierarchy, the thing at the top is called a root, or if you want to follow the family tree, a parallel, the top of a hierarchy is literally called a parent. Anything that branches off from that device or that entity is verified by the thing above it. All things in a hierarchy are centrally verified. And this is another major theme of secure, especially enterprise networks, is it's not just guaranteeing that everything can reach where it needs to. It's not just making sure that everything can get to where it needs efficiently, but also controlling who and what can do what and where, right? Centralized management is a incredibly important concept, especially getting to the meat and potatoes of the Sec Plus in terms of actual security handling and monitoring. Centralized everything is essential because as opposed to a more what we would call decentralized network, a network where there is no single device or there's no central way of monitoring or I don't want to say dictating, but that's what happens in networks, but determining what can happen, essentially setting the rules. Unmanageable networks like that they can get away with a lot more things. Accountability goes way down. How can you make sure that everyone's doing what they need to do when no one is centrally managing everything? That's what management's job is. Same thing with networking, right? So before jumping into that topic, but kind of as a preview, but again, routing infrastructure, as I said before, different address for different kinds of communication across different kinds of places, right? So your switch is entirely local network, right? Your switch allows different devices, different people in the same neighborhood in order to talk with each other, right? Think of you and everybody that lives on your street or in your town, right? That's what a switch is going to manage the addresses for, right? That's what the addresses of a switch do. They're the local part of the local network. This local network segment, which we'll transition to in a second. IP addresses are for network to network communication. So the second you need to communicate with anyone outside of your town, outside of your neighborhood, in a different network or network segment, you need IP addresses. That's what your router does. So network to network forwarding. Now, like I said, Given that Sec Plus is very surface level with these networking concepts, they don't go into the major protocols that are kind of doing the heavy lifting that routers do in order to do this. Because, like I said, one of the big things that a router does is it maps. It tries to measure distance with things like EIGRP, RIP, distance vectors, and stuff of those nature. But the Sci Plus, again, for now, just want you to understand the basic premises behind those. We do have two addressing protocols that are currently in circulation for routing, IPv4, which is the older one, and IPv6. IPv6 is very similar in that it's a numerical address separated by dots called octets. It's newer, it's new enough that it's not currently the standard. Essentially, the main difference between the two is that, like anything, IPv4 has a finite number of unique addresses. There are only so many addresses you can give in a protocol because they're a finite number. Like for specifically, right, an IPv4 address is known as a 38-bit address, right? A 38-bit address, where IPv6 much bigger. That bit size, or whatever bit size of address we're talking about, dictates how many unique addresses there are, right? IPv4 actually ran out a couple of years ago. It's been more than a handful of years ago at this point, um, but it can continue to be used because, well, frankly, um, if you think about the internet, right, a lot of IP addresses, most IP addresses that are being used on the internet. Not all devices stay permanently connected to the network and connected to the internet. As long as these IP addresses keep getting, freed up, as long as devices keep disappearing, those IP addresses can be reused by someone else, and the protocol can keep being used, right? Probably not until we get to a certain density of new devices, like kind of what smart devices did. Smart devices are being one of the main reasons IPv4 actually ran out. Well, we actually need to make a hard shift to 6, but 6 is there, and 6's capacity is astronomically larger. Right? Supposedly, this is a metric coming from someone. Couldn't tell you exactly from whom, but something like IPv6 has so many unique addresses that the sun will probably burn out and die before we run out of the number of unique addresses in that range. How believable that is, who knows? We'll see. Technology evolves rather quickly, but that's just to get your mind wrapped around that concept, right? VLANs, virtual networks. So, unlike a normal network, right? Devices that are part of the same network segment, they are associated with each other because they are connected to the same switch, right? Going back to the slide, the switch is what determines that we are on the same local network, generally, the same segment, right? The same neighborhood. However, a VLAN uses software and layer 3 protocols and devices, like your router can do this, where your router treats other devices as if they are on a different network or segment entirely. So you can have devices on the same physical switch treated as if they were a part of different places entirely. You can actually zoom in on this here. Right. On this switch, we have VLAN 32 and VLAN 40. All of those devices are physically connected to the same switch. Without using a VLAN, they would be the same network. They would be considered the same neighborhood. But VLANs, a virtual LAN, is network segmentation. More specifically, logical network segmentation and you could pretty much quote the exam saying this at this point, that allows devices that are part of the same physical infrastructure to be treated as if they were part of separate. But this gives us a couple of different benefits. I'll actually save that for when we get to the slide that actually outlines it more because, well, it ends up being a pretty big point of emphasis for the Sec Plus. A lot of the questions you would see, a lot of just the subject matter from this section, the next lesson, and a couple around it do centrally focus on this concept of subdividing your network and having devices act differently, just for the sakes of traffic organization, and then how that applies to security. But we'll work our way up to and through that. So, attack surface, right? Making the transition from basic network concepts to how does this integrate with security and security concepts, which is the main thing. So, Your attack surface is made up of your total number of what are called vectors. A vector is any potential weakness in your computer, your network, period, any potential weakness. Now, the nature of that definition does mean that a vector is nothing that is guaranteed. A vector is nothing that is, it has been hit before or even could be hit. It's just a potential weakness. Like a lot of analogies for this, but one I like to use is imagine there's what seems like a hairline fracture in one of the walls of your house, right? That's a vulnerability. That's a weakness. But because it's a hairline fracture, because it doesn't seem to go from the top of the wall to the bottom, it's a weakness, sure. But is it one that is potentially bad? Not necessarily. It's just a thing that's there. If anything, it's a cosmetic damage, but you identify it as a weakness because of what it could potentially be, right? So your attack surface is made up of all of these things, and that can and practically does. That makes attack surfaces very difficult to fully grasp, especially considering kind of one of the main topics of the Sec Plus in the context of this little seminar is just frankly understanding one of the more difficult parts of infosec of computer security period is trying to fully encompass the sheer numbers of vectors that exist, not just in a computer, because that's hard enough, but the sheer number of total potential minor to major weaknesses that exist in an entire enterprise infrastructure is difficult, if not virtually impossible, most of the time, right? Because if you just think of it practically, how many potential weaknesses, small or large, exist in every single device? Not just every single device, every software that all of those devices use. Now you extend that to the network, how the network is connected, how the network devices are configured, how the network devices are placed, and all sorts of different things going up and through the radio frequencies that certain wireless devices use and the power fluctuations of the power cabling also contribute to vectors. So it gets quite insane, and it is, right? Generally, if you ever have to ask your, if you're ever musing and asking yourself the question, how do we know all of these security vulnerabilities? How do we know all these concepts, and yet they still manage to get exploited? They still manage to get, these vulnerabilities keep getting used. It's because the vector surface is often much larger than anybody can literally account for, and attackers find new ways to use old tricks in ways that it's impossible to predict everything. So we at least need to have good ways of responding. So, one broad concept that does help us as much as possible is this concept of defense in depth, right? Understanding that it is impossible to completely map out all vulnerabilities, all vectors, all things that could possibly happen. What helps us dramatically is having overly redundant, no, definitely not the word overly, but redundant layers of security. When you're talking about security devices, which we will be, at least an introduction, at surface level, a lot of security implements almost sound like they're doing the same job. They do a very, very, very similar job, like a firewall and an intrusion prevention system, for example, those two especially, right? When it comes to security, it is never a better mindset to think, well, if blank can't do everything, I should never use it. It is always best to think the opposite, defense in depth. Well, if a firewall can't handle everything, what other device can cover its base? And I will use both of these things. Obviously, real world practical limitations do apply, like budget, time, people that are actually trained to utilize these things. But when it comes to securing these size and complexity of networks, you need defense in depth. Otherwise, no device is perfect. A another common type of class that I personally teach very frequently are offensive security classes as well. And it's not an understatement when I generally tell those students, if you're just using a firewall, just and only a firewall, we can go over in the span of 10 minutes, very quickly, just 10 different methods of tricking, bypassing, or probing a firewall to help you get past it. You need more devices for more complex compromise. So, what are some general things that help to contribute to these vectors? Single points of failure is a pretty big one. These are not entirely avoidable because there are just certain things that we implement for convenience. And convenience always contributes to ease of access, which is a vector, right? Like single sign-on, right? Having one set of credentials to access several different things. Because inversely, if we didn't, people are really bad at memorizing new and unique passwords, right? Shared accounts is another type of single point of failure, but again, so inherently useful that we can't just get rid of all of them. It would actually be more detrimental to not use them at all. So another thing that we have to end up doing with dealing with our attack surface is balancing out things that on paper are not good, single points of failure, but because not having them at all would be worse, trying to find that balance, and that can also be very difficult because it depends on context, it depends on what does your company do, how does your company work, and the way that your employees work, and there's a million other factors, right? What is a good amount of single point of failure implementation that is good for you that may not be right for someone else? So it's also hard to sometimes find standardized answers that best fit literally everybody because that can become impossible. What else we got? Complex dependencies. So a lot of what I would say follows these, those next couple points we'll be getting to as we go through stuff. But, you know, the inherent complexity of all of this additionally contributes to why is this so hard, right? Everyone can relatively easily Google, SQL injection. Everyone can learn in the span of 10 minutes the basic gist of cross-site scripting, but that's a tip of the iceberg kind of scenario, right? What are all of the possible potential ways that these attacks can be injected? Go far beyond what people can learn in a cursory glance, and sometimes over years of experience, because hackers keep finding new things to do and new ways to trick things. And as we develop new technology, they find patterns. And I'll even tell you, just as a very very boiled down and brief explanation of years of offensive security, is it does tend to come down to pattern recognition. I will just tell you that, right? Attackers find these patterns of between things that we've done before and new things that we're doing. They find these patterns and they find links. These links of behavior, these patterns that they recognize, contribute to exploits that they use, right? What seems like a basic concept that everyone can Google in 5 minutes, SQL injection, gets applied in a new way because this new technology has a pattern that's similar to something we've done before. Obviously, the attack might need to get tweaked and modified a bit, but that's kind of why it keeps happening. Not always, but trust me, these patterns that people recognize tend to be what causes a lot of stuff. Hell, just in general, when it comes to overall infosec security, anything that works on a repeated pattern is generally a bad thing, right? When we think about encryption, encryption wants to be as random as possible. Predictability and repeated patterns often, well, are the exact stark opposite. But anyway, security zones. Speaking of network segmentation, so as I was saying, right? Network segmentation generally means the any and all methods of subdividing how your network functions, how it communicates, and how traffic is kept, well, separate in its own distinct zones. Right? A security zone is a network segment that you have applied a certain a level of security to. Another way to rephrase that is you place devices in a zone that have a shared level of security to them, right? One of the most common, if not the main one that you would generally see discussed and hear about is called a DMZ, a demilitarized zone. The DMZ, the shared security level of DMZ, is public, quote unquote, which if you were gearing up to take the exam, I would have a lot of very explicit things to tell you about. Be careful of your take of reading questions. But a public network segment, public doesn't necessarily mean internet. It's related, but if I refer to something as a public network segment, that doesn't mean that these are devices that are on the internet or on the internet, but these are internet facing servers. Is a phrase that's frequently used. What that means is the kinds of servers you frequently see on DMZs is a web server, an email server, sometimes file transfer servers. Essentially, if the server's job is to go to and from the internet frequently, that's its main thing, those go on DMZs. Those should be placed on DMZs. So internet facing or internet serving servers, that's what they are, right? Now, in a broader sense, scaling back a bit, right? What is the point of just these zones? What's the point of segmentation in general? Same things I've been saying, but we now have not just a way of organizing, oh, internet traffic should go to the DMZ or public traffic should go to the DMZ, internal traffic should go to the internal segment. This also helps us to more meaningfully map and place our security devices when we eventually get there, when we eventually get to them, right? The DMZ, we know since internet traffic is going to be going to and from those segments, internet traffic, internet traffic generally is where we get a lot of concerning stuff, right? Generally a lot of concerning stuff. Like, well, bad people exist on the internet. Hopefully, this isn't your first introduction to that as a concept, but yeah. So knowing that all of our servers that are going to be touching and communicating the internet most are going to be in a central single place, that means that we can focus a lot of our what we call perimeter security around that location, right? Things like firewalls, things like IPSs, things like proxy servers. Because otherwise, if your internet traffic was coming from, well, pretty much anywhere, then that's more bases you have to cover. That's more entryways that you have to cover. By setting up, and this is a very common implementation of DMZs, you'll see a better picture of this later, by setting up DMZs as essentially a choke point, right? The only way that you can get in and out of the network is through this publicly segmented area, means that all bad traffic has to come through this central single choke point. All the bad traffic has no choice but to use this one way in and out. You can focus all of your security perspective on there. And that's the kind of thing that drastically helps with security all overall, because like I said, the sheer number of possible things an attacker could do, the sheer number of ways they can possibly get in, can at least be controlled by limiting the entry points that they have. And that plays a big role. So, public versus private, generally the most simple distinction between those two terms as security zones. A public network segment is going to be your DMZ, right? Things that are going to and from the internet. Publicly accessible, think of it that way. Private segments are your back end, as we call it. This is where most of your other servers and your private network, so your workstations, you're actually where people are working in and out and to and from, that kind of thing. That's what that's going to, well, that's what that's going to represent. So generally, you will have a lot more private network segments, more private security zones, because the DMZ is the DMZ. You need internet servers, you're going to have a DMZ, maybe a second one. But when we talk about internal private zones, we're going to have things divided by stuff like our business units. Like this is the HR segment, this is the administrator segment, this is a management segment, right? So within that local network segmentation, we can also add different layers of security. So I've used a term that's going to be emphasized more as we go, but perimeter or perimeter security. These are devices that protect traffic coming in and out of the network generally. Things like firewalls and IPSs, intrusion prevention systems. When we're looking at our internal network, there are other things we can do that can also control how traffic goes to and from where and how. Because, like I said, a network segment well, let's go into it a little bit more. When you create a VLAN, right? When you create two VLANs, VLAN 1 and VLAN 2, just by setting them up, VLAN 1 cannot necessarily directly communicate with anything on VLAN 2. You actually have to set it up so they can communicate. You have to bridge those communications, right? However, that is not very secure in and of itself. It does something, but what we call port security can further limit and make much more restrictive access, define much more restrictive access between different parts of your switch network, of your local network. So just focusing on the switch, because there's a lot more to this than we can summarize here. Just focusing on your network switch, let's say Marcus's computer and employee number two's computer are connected to the same switch. If employee number 2 and Marcus are part of completely different levels of clearance, of security, Marcus is an admin and employee 2 is just a basic level employee, then employee number two's computer has no reason to directly communicate with me. There's no point. Plus, I'm an admin. There's a lot of dangerous things you can do if you can just directly access, admin stuff. So a broad category of controls called access controls literally network access control, NAC. Network access controls are explicitly about controlling these kinds of things, right? Employees of a certain permission level can talk to so forth, so on, and so on. Employees at a different permission level can talk to this place, and some other place. And then just making sure that those permission levels are adhered to by devices as well as programs that they would use and tying those to users themselves. So configuring these restrictions on your switch's ports is a big part of what this is. Again, a lot more to that than we can summarize just here in this 2-hour lecture, but that's the premise, that's the idea. So other than what I've said, I mean, these next two slides just kind of summarize a lot of the points that the conceptual points I've been making. What are other factors that determine, what devices we can have, and especially considering defense in depth is having multiple of similar devices? What are things that, frankly, meaningfully limit us from from doing everything? Obviously, cost and physicality. There's only so many things we can buy because there's only so much budget we have. When you start looking at these major security appliances that can do more and do as much as possible, you start looking at some pretty hefty bills, and not everyone can support that. Plus, there are maintenance costs associated with them and things of that nature. Not only that, you have to have the people that can actually be trained to use them, because you can have the best system on the planet, but if no one knows how it works, then it can be functionally and practically useless. Other than that, we have compute responsiveness. How resource heavy is this thing? Because again, the best utilities on the planet are going to take a lot of memory, a lot of network bandwidth, and some networks are already really, really busy. Some networks are already completely tied up with what they're doing. You add this latest and greatest whatnot thing to it, you could cause your network to be unusable, unfunctional. So compute, utilization of these things. Scalability and ease of deployment, partially what I was talking about, right? If no one knows how to actually use your thing, or you have a new implement that you're thinking of, well, putting in, integrating, but it's not easy to add it on to what you already have. This is this is a measure of scalability, right? On the contrary, a highly scalable network or something that is highly scalable means that you can generally just tack it on. You kind of just add it onto an existing thing without much difficulty whatsoever. That's highly scalable, right? You can make an extension pretty easily. So how easy is it to integrate this thing into what we already have is also a pretty huge factor. And very often, all of those things and these next handful of things are very valid and common reasons why we can't get or we wouldn't get something that you might call the best or preferred even, right? Because we simply can't. Availability. Integrating new things does often cause existing things to have to go down temporarily, right? Whenever you update something, whenever you make especially major system changes, you're going to be turning something off while you're making changes. You're going to be disabling something while you are integrating a new thing. So how long or how major that disruption ends up being is another reason why we may not get an implement at all, or at the very least, we would delay very much more often. We would delay the integration of a new thing because, well, let's say we're currently going through our peak business season, right? We're not going to start making major infrastructure changes during peak because any disruption during that time is going to be significant loss. So we might have to delay integration, if not entirely, entirely reconsider. We at least have to delay it for later. Resilience and ease of recovery, absolutely. A very big difference between a device that you can, let's say, two devices, both of them crash. One device takes 12 hours to recover, the other takes 10 minutes. One of those is generally going to be seen as preferred, especially if those two things do the same job, because, yeah, minimalizing downtime, time is money, time is functionality, and these things matter a lot. Right? Patch availability. That's an issue that's going to extend to the very last section that we're going to get to eventually. But yeah, what we're generally going to refer to as patch management as we go. How easy is it to update, patch, and how does that affect other devices in the network is another huge consideration. Generally, as a summary, because if you want some real world examples of why patch management is important, look at the latest CloudStrike fiasco. Right, a major part of what was going on there, or the issue was with patch management. Essentially, a patch that this CloudStrike thing put out, this update that this CloudStrike thing put out, was incompatible with Windows, the operating system that everyone and their mother uses, right? Good patch management is a couple of different things. It's making sure that you update things when it's available, but almost more importantly, when patches need to get put out, when updates for a program need to get put out, that those updates themselves are tested. Because what happens when you don't test a patch, a thing that changes the coding and function of a major program? Look up the CloudStrike fiasco, right? It can, at worst case, this central core platform becomes incompatible with the single most commonly used operating system on the planet, and then you have a DOS of literally historic scale, right? Test your patches, because patches can cause things to become unstable. Patches are supposed to fix things, but that doesn't mean that they won't cause incompatibility problems. So, next section starts on our appliances. Probably take our break halfway through here. Just to clarify, about an hour through this, we're going to take a break so we can stretch, go to the bathroom, and all that, and then we'll do the tail end. But anyway, so as I was saying before, placement has a big role in how security devices do what they do. So much so that if certain devices are not placed properly, they can be entirely non-functional, right? The primary types of devices that we'll be focused on this short little discussion are going to be what are called edge devices or perimeter devices. These are the devices that are primarily responsible for preventing things coming from and to the internet, right? As opposed to, like I said, what's called NAC, network access control, which are going to be a lot of security controls that focus on how traffic travels within the network. That's going to be expanded. That gets expanded upon in the full Sec Plus. But for us, that just means we can focus mainly on common devices that people are at least familiar with at a surface level, depending on your experience level, of course. So, device attributes. What they mean by this and the things on this slide are, regardless of the specific kind of device, perimeter devices tend to require a couple of different things, right? So a lot of these devices may be referred to as active or passive. These are terms that get used very frequently across all sorts of devices, not just perimeter devices, but an active device is one that is currently functioning, it's currently on, it's currently doing its job, right? It's a firewall that's blocking and preventing. A passive device is one that's sitting as a backup, more or less. You see this term used a lot with availability and redundancy concepts, where if the primary thing fails, has an outage, or goes down, the passive thing can automatically essentially take up its place and continue the service running, preventing, causing, higher availability. That's at least the idea. Right. Generally, when you're dealing with very large infrastructures and you have all of these different points of failure, intrusion, compromise, and whatnot, it's very important to have at least some passive utilities, because of the fact that you cannot guarantee when and where things will go bad in a network that size. Inline is a very important concept. So any device that has the ability to filter traffic, prevent, allow, whatever, needs to interact directly with that traffic. So you see in this diagram where that device called a tap is. That tap is currently in line. All traffic going to and from that switch, generally, needs to pass through that tap. That's the only way to get to that switch or anywhere else, right? In order for that tap, if that tap was inspected, I mean, hell, there's a firewall literally right next to it. So that firewall actually being the thing we're talking about here, in order for that firewall to inspect anything, traffic has to go through it. If you saw an alternate line, an alternate way to go around that firewall directly to the switch or directly to the tap, that firewall can become useless instantly. Firewalls can't magically inspect traffic that doesn't pass through it. It has to go through it, right? So these perimeter devices, these edge devices, are entirely reliant on their placement. They can only inspect things that go through them. That also means that they have another inherent weakness, firewalls being the first one we're focusing on, and that is they can't really help you with what we call insider threats. Any kind of bad thing or situation that happens entirely internally, right? It happens from an internal machine and it only happens to other internal machines. The firewall is entirely blind to it. Inline devices only inspect what comes through them. If it never does, it never knows. We have other devices that keep us aware of the internal network, because these perimeter devices can't help us in those inside threat situations. So a bit about firewalls and a couple of their common flavors, a couple of the common different types of firewalls, because many devices that do the same thing but have a particular focus and emphasis where they specialize. But anyway, so a firewall is a device that uses a list of rules, literally called an access control list, a list of rules that controls access to and from things, that blocks or allows traffic based on that set of rules. More explicitly, this ACL functions as a whitelist. This is a list of rules of things that you explicitly want to allow to happen, right? I would like traffic to go to and from here, 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 and here. Those 5 things. Any traffic that comes through or that tries to communicate through or to or from anywhere other than where you specify gets automatically blocked, denied. If it's not explicitly allowed, it is implicitly denied. An important part of any whitelist is this implicit deny rule. If it's not explicitly stated, assume that it should be blocked. That is the basis of how these firewalls work. This is a list of rules. The main difference between the different kinds of firewalls that we have are what they emphasize on. Because base level firewall, what we would call a layer 3 firewall, only inspects based off of IP address, port number, and protocol. Basic layer 3 and layer 4 things, addressing information. So the most basic kind of firewall, where's it going to, where's it coming from, that's all it knows how to check for and block based on. A layer 4 firewall, also frequently called a circuit level gateway, focuses very specifically on a protocol called TCP. TCP is one of our major transport protocols. TCP's job, amongst other things, is to guarantee delivery of traffic to and from various places. But layer 4 firewalls focus very precisely on TCP communication because it's generally our most prevalently used protocol for delivering traffic anywhere of most types. It focuses just on that kind of traffic, TCP handshakes, TCP functions, because, again, as a watered down summary, a lot of probing, a lot of scanning and reconnaissance that attackers do tends to involve manipulating and modifying the TCP protocol for various ends. So, again, firewall for a very specific focus that has a high prevalence associated with it. Layer 7, this is where we get our biggest variety in our more advanced firewalls. Application layer firewalls actually have the ability, they tend to have the ability to inspect the content of traffic. Because up until this point, firewalls mostly just look at address information. Where's stuff going to? Where's it coming from? And that's pretty much it. What's called deep content inspection is the ability to look at the data, the payload that comes with the packet, not just the address that it's headed for, not just where it's going to or from, but what is its content. That's what you need these guys for. So for example, any situation where, this is a common one, any situation where you would need to inspect emails for malicious attachments that could be malware, that has to be a deep content inspection device, what we might call an email gateway, a type of layer 7 firewall that can look at the content of an email, not just who it's getting sent to and from. Our next device that we're going to briefly talk about is a proxy. Proxy servers are forwarding servers. Their entire job is forwarding traffic received from somewhere to somewhere else. In this way, they function similarly to routers, but proxies don't fully define your network. Firewalls do a bit more. Firewalls kind of represent your network as a whole. Proxies are just used to forward from one place to another, from one device to another. A lot of different use cases. The two main types to emphasize this, forward and reverse, depending on whose traffic we're trying to forward. So for a forward proxy, this is for internal network traffic going out. Like let's say one of my employees' machines needs to go out to the internet. That's forward mode. This is useful because, as a general rule, you never want internal private and protected machines to connect directly to the internet because, well, that's kind of dangerous if you think about it, not even think about it, right? And reverse is the opposite direction. Outside traffic that is requesting something from me, from within. Here's another practical question that kind of answers itself, right? does the bank, let's say, any online banking application that you would use nowadays, does the bank want your device to connect directly to them? Hell no, to say the least, right? No bank on the planet wants any internet device to connect directly to their servers. So how do you get your bank account information from your app then? A reverse proxy. A reverse proxy is the stand-in. Your banking application connects to a reverse proxy. The reverse proxy retrieves your bank information and then presents it to you. This makes it so that you can get the stuff from the bank without connecting directly to the bank, keeping them safe and you out of their network specifically. So it's a matter of, again, direction. For the internal network, for the network that's being accessed, is it internal traffic going out or external users requesting something in? So, what we call IDPS systems, intrusion detection and prevention systems. Intrusion detection systems are detective devices. Their job is to monitor your network and keep track of things that are happening, plain and simple, right? Network visibility is a big thing here. IPSs are much more similar to firewalls. They are perimeter devices that must sit in line with traffic to inspect them to prevent things that you would define as bad. The difference between these guys and firewalls, however, is the way that they inspect traffic. They look at traffic in a different way, right, in order to prevent different patterns of malicious traffic. So, where a firewall just mostly looks at where traffic's going to and where traffic's coming from, IPSs can recognize a specific package, like, for example, the I love you virus, very well known virus, all things considered. IPSs can recognize the I love you virus because of how it is structured. The actual binary of the I love you virus is unique. We call this a signature-based detection. Firewalls do not do this. Firewalls can block suspicious traffic, but firewalls don't know what the I love you virus looks like. That's what IPSs can do. If you're wondering, that sounds very similar to antivirus, anti-malware. That is the exact same way that antivirus and anti-malware works, except this is better suited for network intrusion, for essentially anything coming from network interfaces. Similarly, IPSs also can look at patterns of behavior to determine malicious activity or things that you would want to prevent. Things that we will call abnormal or anomalous. Essentially, if you define what normal traffic should look like and patterns that traffic should take, IPSs can notice anomalous behavior, something other than normal, and actually stop that. That feature in particular is very useful for what we would call a zero-day threat. These are viruses and malware that are so new that there are no detectable means for them yet, except because 0 days are so new, because they're brand spanking new, they always look anomalous. There's no way to say that a 0 day ever looks similar to, well, I can't say that necessarily if we're talking about some caveats, but by definition, a 0 day is so new, no one recognizes it. So this type of IPS called behavioral, this thing that always looks for anything abnormal, something it doesn't recognize, actually can stop them pretty consistently. You just need to have the right type of detection. Again, this is why defense in depth is so important. Firewalls don't do any of that. Firewalls are useless against that kind of thing, more or less. So you have a firewall, you have an IPS that has whatever secondary means of detection you need, and you put them back to back. You use them in conjunction because they both cover very different bases. Next, what else we got? We got load balancers, mostly focusing on the concept of load balancing. So load balancing is distributing workload across entities that are doing the same work to prevent a single device from overworking itself, from crashing, right? Like web servers. Web servers are very busy types of servers, right? Instead of having a single web server for a very busy shopping site, you might have 3, 4, or maybe 5 that are essentially clones of each other. They don't need to be different because their whole job is to share the workload of the website, right? Now, the concept of load balancing can be done in a lot of different ways. However, a dedicated device called a load balancers can give you advanced automated ways of distributing workload. They essentially have the ability to detect what's called weight, Waiting is essentially what I'm referring to as workload. Server 1 is currently at near capacity, so it automatically sends it to server 2. If server 2 is at capacity, it sends it to server 3, so forth and so on. Along with this ability to detect workload, they also have these scheduling options which help them prioritize certain servers over others, like round robin or session affinity. Session affinity, for example, being keeping a user consistently connected to the same server that they are connected to in the first place when that is appropriate. So again, giving additional tools for priority and automated detection is what a load balancer, a dedicated load balancer, does. But the concept does extend beyond that. So a web application is one of the most common examples of a application layer firewall. A WAF, its job is to inspect HTTP traffic. This is something that you commonly see, and as a good common example, this is a good example of a layer 7 firewall because there's a lot of different network protocols on layer 7. HTTP, there's FTP, there's a lot. There are so many. What you often see with layer 7 firewalls is specialized ones. Multi-protocol firewalls do exist, but they are usually prohibitively expensive a lot of the time, or they're just less common. What you more often see is ones that are specialized to a common type of traffic, like any and all things going to your web application, your website. So WAFs are an ideal choice, an ideal type of firewall for inspecting all sorts of malicious behavior associated with web browsers, web servers, anything targeting the database that your website uses, and all of the attacks and vulnerabilities that would target these parts of your network. Right? Web application means HTTP. Rightio. And that gets me to another title slide, switching topics to remote access. Halfway point. I'm also at the top of an hour, so let's go ahead and take that 10 minute that break I was talking about. Yeah, we're just going to use the same 10 minutes I usually use during my classes, and we'll do that. So yeah, let's take a quick 10. I'll put a timer up on screen for you. Come back and we'll look at the second half of this little lecture, going from remote access to cloud to a couple of other concepts, but those being the primary ones. Right. So I'll see you in a little bit. Put a timer on screen so you know generally when to expect me back in my seat and all that good stuff. Set it to a little. Oh, set it 10. Leave it at that. Okay. All right, we'll get back into. I'll get the slide back up just in 1 second, and we'll get through the rest of all of this. All right, good enough. So that left us right here. Good. Getting back into it. So, we have this next little section called remote access concepts. Like many other things, are touching on this, but these are technologies associated with, involved with, allowing us to access networks remotely. As you know, building off of what we were talking about, the basics of how routers work, allowing us to talk from one network to another. We can do other things to expand that relationship. So, VPNs, starting with that. VPNs form kind of the basis of most of our means of remote access nowadays. In a similar way that VLANs make it so that devices on the same physical infrastructure are treated as if they're completely separate from each other, VPNs kind of actually do the opposite, ironically. We have devices that are physically on separate infrastructures across the internet, across whatever boundaries you can think of, that are treated as if they are part of the same network now, to get the same types of security applied to them, to be managed centrally, and all sorts of things. This is the same technology that allows us to, quote, remote in to the office and stuff like that. There are two primary ways of doing it, so to speak, though there are obviously more. Client to site, which you see on the bottom, this is remoting in, this is remote access. I'm at my home and I can remote access to the office wherever the hell that is, right? Using a VPN tunnel, and then a site to site where we might have a branch office, the top example, or we might have a branch office that we don't need the network to function differently. I want the branch office's network to essentially be an extension of the primary office. That's what you use this VPN for. So this entire other network is treated as it's just a segment of another one somewhere else. Similar premise. VPNs are named as such what they are because of their tunneling ability, tunnel. What they do, as opposed to what normal internet traffic does, is VPNs allow us to designate point A and point B across the internet. Normally, when you're sending traffic across the internet, it's essentially like a giant relay system, right? In order to get to google.com, your traffic actually goes from your router to some random public server to another public server to another public server, because you don't actually have a direct line to anywhere on the internet, not usually, right? In order to avoid this, for various reasons, traffic efficiency, but also security, right? You can make it so that your traffic goes directly to this other place on the internet by setting up this tunnel, right? You're tunneling through the internet by doing this, right? This does inherently add a little bit more security to your traffic, because now your traffic isn't relying on these public services that every other internet traffic would use, these public servers that are well known. Your traffic is now using this dedicated connection that you get to define and you get to set up. By itself, it's not the most secure. It adds, but just by essentially having your own designated point A and B, it does do something. Now, on top of that, where we get to see tunneling be very secure, actually secure, is when we add encryption, authorization, and security protocols on top of this. These are what we refer to as data in transit protocols, and their primary job is to add additional layers of security on top of these connections from point A to point B, data in transit. So, TLS is your de facto any and all things going across the internet, right? It adds encryption, the making it so the data cannot be read when it is intercept. It cannot be read in transit until it reaches its destination, as well as various forms of authenticity, which largely have to do with proof of identity. Like, how do I know I'm talking with the device that the device says that it is a lot of authenticity concepts and controls. So, confidentiality in the way of encryption, making it so that only approved A and B can read this message, but also authenticity, which makes it so that we can trust who and where we're talking to, given The internet is made up of a bunch of people that are going to try to pretend that they are us or someone else, right? So, other than TLS, VPNs in particular, VPNs actually have a wide selection of things they can use to secure them, protocols that they can use to secure themselves. VPNs, however, have their own unique protocols. TLS can be used for just about anything going across the internet, HTTP, FTP, so forth and so on. A protocol called IPsec, which is named as you see up top, Internet Protocol Security. IPsec is used exclusively for VPNs and adds additional features, and it's just better geared for what VPNs want to do, right? A big part of how VPNs function is setting up this explicit connection between A and B, setting up this explicit route between A and B. So a lot of what IPsec does, similar to TLS rather, is adding encryption, adding authenticity methods, but also helping to facilitate the connectivity that is necessary to set up a VPN in the first place, right? Not all internet protocols like HTTP set up these dedicated connections like VPNs do, so IPsec is geared more towards that. Within this IPsec protocol, there's also a bunch of other components, other essentially protocols within the protocol that are made to help facilitate each of these little distinct functions. Essentially, one of them is called IKE, IKE, right? So, like SSL, TLS, and SSL rather, you can see over on the right something called an authenticity header and an ESP. IPsec also has different modes of operation because there may be reasons why you might not necessarily need your traffic fully encrypted and fully protected because this is it can affect performance actually. The more encrypted, the more heavily wrapped up, so to speak, your traffic is as it travels, the slower it tends to go. The more something is encrypted, the more layers of security you add, the more tunneling that you do, the longer it takes to unwrap it on the other side. So situations like that and others, you may not necessarily need the most secure version. So IPsec having these different modes is very, very useful for these different variety of use cases, right? Especially considering that we can forward traffic not just across the internet, but you can set up VPNs and VPN-like tunnels within your local network for traffic efficiency again, right? In the same way that the internet doesn't usually allow you to directly communicate from A to B, your internal network might not allow that either. But there are reasons why connecting directly from A to B is useful in your internal network as well. That actually works as a segue for SSH. SSH is another data in transit protocol, security protocol, that makes data unreadable in transit, same as the other two, but is associated with a very specific use case, and that is administrative traffic. This is the protocol, generally the de facto protocol, that is used to send and receive commands from admin devices to other machines. The basic premise, the basic process is I connect to your device using SSH as a tool, as a protocol, and then once this SSH tunnel, similarly to how you would set up a tunnel with a VPN, is established, I send admin commands through this tunnel. That is what SSH is explicitly used for. So very much so, like I said, we can establish these explicit point A to point B connections within an internal network. SSH does that, but for administration, very specifically. Right? Otherwise, it implements similar functionalities to things like IPsec and TLS, where it also has authenticity. When I try to connect to another device with SSH, it will actually ask me for credentials. It doesn't just let you connect to somebody and then start sending commands to them. You have to prove your identity. This is a central necessity out of any good security data in transit protocol is proof of identity. Other things that SSH does as well is that it implements asymmetric cryptography concepts to better facilitate its identity proofing. These things called public and private keys essentially are another means of recognition. If you can see in the screenshot I have on the left here, this error says something about along the lines of this key is not recognized. What it's essentially saying is that this person tried to connect to this device with SSH, and SSH is giving them a warning. Their device is giving them a warning saying, hey, we expected a certain key. A key can be used to identify a device uniquely. We expected this key, but that's not what we got. We got this other thing instead. You might not want to trust this device, right? It's essentially like saying we don't recognize this thumbprint, we don't recognize this signature. We were expecting A, but I don't know what this other thing we got pertains to or who this identifies. Right? That is an authenticity check that was failed. Authenticity, again, being a proof of identity check, otherwise came back bad in some way. Next, we got out of band management as a concept. So out of band means using a route other than the common or primary route that traffic would normally take. So instead of taking a highway that everyone would take, I take a side road because I'm local. I'm local, so I can take the side routes when the highway gets busy, because the side routes are going to end up being quicker when traffic gets heavier, right? Think of it like that, as out of band, right? If everyone is using the internet browser to log in, I'm going to use my cell phone, my cellular data plan, as an alternate channel, or a side channel is what this is also called. Now, out of band applied to management is essentially the use of SSH that I just actually described. So for various reasons, admins find it much more useful to directly connect to the devices that they want to issue commands to, as opposed to using the network the way that it is normally laid out. Because, like everyone else, admin devices would have to use your local switch. They would then have to use the router to go to the internet. Then they would have to use the router to go through the internet to go somewhere else. But if the admin uses tools like SSH, essentially like an internal admin VPN, the admin can set up an SSH tunnel from their machine, point A, to the device they want to issue commands to, point B. That allows much more efficient communication. Not only that, the security benefit here is very big. If there is a type of network traffic that you really don't want attackers to be able to easily get access to, one of those types of traffics is going to be admin traffic, because getting access to admin traffic means you can see the kinds of commands that are being issued to this network, and which ones are available, or which ones are valid, which ones will work. But also, just in general, admin traffic is very useful on all to an attacker, right? You see the admin traffic itself, but also, again, the things you can request servers do for you, which leads to a lot of compromise. Literally, we call that command injection, right? So other than just relying on SSH as the tool itself, like a software-based tool to connect from A and B, we have proxy servers that we use to help to facilitate these connections. What are we often called jump boxes or jump servers? They are proxies that are dedicated to this general thing that we've been describing here, right? Just to facilitate these connections in larger number, to essentially ease the use of this as a tool and a process. We don't necessarily need a jump server when using SSH, but jump servers very much help us when we start looking at these larger enterprise networks with many network segments. They just kind of make it easier to do. You would SSH connection to your server. The jump server would then forward your SSH connection to wherever you want to go. This functioning as what we've previously called as a forward proxy. Internal traffic getting forwarded out somewhere, but staying within the network, still a forward proxy. We're forwarding an administrative connection, an SSH connection, right? Which is why these are primarily referred to as SSH servers, but any remote protocol can be used to generally do this. I say any, but depending on the nature of your remote access, other kinds of protocols can be used here, like RDP, a Windows exclusive remote access protocol, not often associated with administration, but associated with remote desktop access. RDP servers are the same, just with a different protocol. And the last little section I got for us to kind of wrap things out with is an introduction to clouds concepts. Right? Something that's definitely been more of a shift in recent years, especially with CompTIA certs, but kind of every cert just in general, is more of a focus on basic cloud concepts, given cloud's overall prevalence in everything that we do nowadays. So as a basic premise, cloud in its simplest form means remote access and utilization of a service of something that is physically hosted by a third party. Without the third party facet, you're not really looking at cloud, you're just looking at remote access, right? Though the two terms are not divorced whatsoever, right? So there's always a third party involved. All cloud services are what are frequently referred to as unmanaged and metered or measured services. What those two terms mean is that unmanaged means that regardless of what kind of thing you are renting from the cloud provider, there are things that you don't control. That's the whole point of it being third party rented utility. Right? And a metered service simply means that at all times, the cloud provider is keeping statistics on use. How much of the resources are you using? Whether or not you're hitting capacity and general statistics of how you're using their service so that they can better facilitate a couple of different things that we'll emphasize as we go through. So taking the Sec Plus, and actually most of these InfoSec certifications nowadays, something you'll run into across all of them, even low level ones nowadays, is what are called service and deployment models. We're going to be pretty brief here, because generally in terms of the concept, you can get the concept across pretty simply. The the deployment models have to largely do with exclusivity. They are often tied to security, so we'll focus more on these. And the service models have more to do with your responsibilities and your amount of control and involvement with the cloud service you're using. Like essentially something like Gmail would be what we call software as a service, which is relatively uninvolved. You don't need to know how an email server works to use Gmail. You just make an account with credentials you made up in 5 minutes, and you get to send emails like you're an expert, like you know how an email server works. That's a true unmanaged service. Now, focusing on the deployment models, we have public and private, two primary ones. A public service, again, Gmail is a good example. Once this service is up and running, anyone can use it. Just as a rhetorical question, right? Who is allowed to have an @gmail.com email address? Again, anybody. It's a public service. Private service, this cloud service is only usable by people that belong to a group, that is employees of a company. So my employees have this cloud resource they use for collaboration, information sharing, but it's just my employees by a certain group, limited to a group. Other things that are related to public and private, and depending on how you define this, are also synonymous with the two. Public cloud services are associated with this concept called multi-tenancy, where your service is running on the same physical server as many other users. Like Gmail, Google is not going to dedicate a whole server to your email, dozens, if not hundreds of users are going to be using the same email server as you. This gives Google a lot of efficient use of available resources, allowing services to be relatively cheap, if not free, because a phrase I use a lot when talking about cloud is prime real estate. If I can get 500 users with 500 users worth of service from one server, that's pretty efficient, and we can provide the service pretty cheaply and available. Private is most often associated with single tenancy, which is much more secure. Single tenancy is traditionally your service has its own dedicated server. This mitigates concerns where other bad things that happen to other users might affect you because your service is on its own isolated server, so that literally can't happen. But you're going to be paying a premium for good reason, right? You're essentially getting a whole network service server dedicated to you that could have been used for many other users. But again, for any kind of client that has these very high security needs, private and single tenancy is the best option for them. Like think of like a government entity. Government entities cannot have any kind of risk associated with public data intermingling with government data. So that's the kind of option that they're relegated to, right? Otherwise, we have community, which is several organizations sharing a cloud deployment, like my company and my company's business partner for the sakes of collaboration and information sharing and whatnot. And then hybrid, which is technically the most common, is going to be any combination of all of the above, which is the most common simply because most public services are free, if not cheap, and widely available, a lot of variety. And private gives you a lot of security assurance and, well, control. So as a company, there are reasons to use both, and it's common to use both because, again, why wouldn't you, especially considering one's cheap, if not free? A concept that the Sec Plus has started testing on more, and is just good to understand generally as a cloud user, more than anything, as well as a cloud provider, is what's called the responsibility matrix. The responsibility matrix has to do with, depending on what specifically these service models over here, software, platform, and infrastructure, one of the main things that these service models represent is what you as a customer versus what the cloud service provider are responsible for. Now, like I said, taking an actual cloud certification like a Cloud 101, CompTIAs, or AWS, or what have you, this is a pretty core concept because, hell, if there's a cloud fundamentals, an important thing that cloud fundamentals class needs to teach you is making sure that you're not paying more than what you need for, because most cloud providers will not stop you from paying for resources you never use ever. So that's a big thing. So things that are always the cloud provider's responsibility versus things that are always a cloud customer's responsibility is a good thing to just baseline focus on. So the cloud provider is always responsible, always going to be responsible for, uh, always going to be responsible for the physical infrastructure, the actual physical network, and anything tied to that. Because obviously, regardless of what kind of service you're using, the definition of cloud being third-party hosted means that Amazon controls the physical AWS servers and the infrastructure. So things that extend from that, any kind of backups of those servers, recovery of those servers, things of that nature, the physical layout and in things of that nature are all going to be the cloud provider, as well as geographic distribution, data centers, again, the actual physical infrastructure itself. This is why, regardless of what kind of cloud service you're getting, all cloud services are called quote unquote unmanaged because you never manage the actual physical part of that infrastructure. You're utilizing those things remotely. Now, the customer, things that they're always responsible for is data in transit. Amazon has no responsibility of how secure your traffic gets to them. Once your traffic gets to their servers, they have full responsibility, legal and otherwise, to maintain and secure it. But how you get it to them is something that you need to figure out. So data and transit security to them, but also identity management is a very big one, right? Amazon doesn't know who your admins are, simply, right? So if you have a cloud service that should only be used by your admins, that's something that you need to set up between the cloud provider, the service you're using, and how the access is going to be determined from your internal network. Because yeah, otherwise you end up with situations of privilege creep, or how did so and so get access to this thing when they're not part of that group. You need to maintain that pretty well. And a lot of things kind of stem from that when it comes to the customer side of things, like you notice user and service access controls, which is the same thing as saying user identity management. Other than that, the settings that you would choose when you're using any given service, like for example, a lot of online services nowadays let you choose a region or data center to pick from, right? Generally, the physical proximity of a data center has a direct effect on performance and performance reliability. If I choose a data center that's over in Alaska, I shouldn't expect high performance because that's really far away. Oppositely, if I choose a data center, let's say New York, because I'm on the East Coast, then I would get much higher performance speeds because that's closer. Cloud providers don't usually select that for you. Some services do it automatically, but that's a quote unquote responsibility or an important thing in terms of performance that the customer does have access to. All right, next we got a couple of just kind of shotgun terms and concepts to get through. So, as opposed to a traditional centralized network, because like I said, centralized networks, enterprise networks means centralized management, centralized monitoring. Being able to control and look at things from one place makes it much easier to just keep track of security concerns, concepts, and whatnot in order to make any of this practical, because again, the sheer size of modern day networks, you couldn't do without centralized monitoring, management, and all of that. Decentralized is when we start expanding beyond the boundaries of a single location, right? As opposed to having one main office, one main headquarters, and that's where everything is, you have remote access. Anything that is remote access of any sort, anything like Wi-Fi, VPNs, anything like that, adds to the level of decentralized there are, because there is a scale. This term is very frequently referred to as deperimeterization. The more wireless remote technologies you integrate, the more decentralized your network ends up being. There are advantages and disadvantages. The disadvantages are being everything becomes harder to keep track of, right? Again, essentially the opposite advantage to things being centralized. Inventory becomes a nightmare, accountability becomes a lot harder, and just stuff like that becomes more intensive when you want to do it well. The advantages to decentralized are, there's actually many. You're not relying on a physical location, so any kind of incident or disaster that would affect the physical location doesn't really disrupt things. It doesn't halt things. Training camp's a good example, frankly, because, well, look at what we're doing now. We're doing remote teaching, right? This is a great example because let's talk about the best case study ever, the pandemic, right? When the pandemic happened, I didn't work less because I couldn't do my job. Like The main office of training camp in Philadelphia didn't have anyone in it because it was COVID was happening. But I've always had remote setup. I've always been able to teach wherever. Frankly, I'm teaching out of a laptop in a discrete location. I'm not even at my main setup right now. This is what mobile is. I don't have to be in a particular location, so I'm not limited by that location, right? That gives you a very good degree of availability and service continuity by having that, as long as it is managed well enough, right? Because again, the inventory and tracking and monitoring becomes more of a nightmare, right? Especially considering how late some of these classes can go, and not everyone in the office is going to be monitoring every class, at these times. So that kind of thing becomes harder. Something else that gets integrated in or implemented as part of more decentralized and especially public networks like the internet is a concept called zero trust. This name is pretty self explanatory, but a basic way to summarize it is never trust, always verify. It doesn't matter who someone says they are, where they're coming from, or what device they say that they're on or they seem to be on. Everyone goes through the same verification steps. Everyone gives a proof of identity. Everyone goes through steps A through Z. Everyone identifies. Everyone confirms. Authorization always, right? This is an important concept for places like the internet because, again, it is generally assumed that people on the internet aren't nice. I mean, hell, the fact that people have that mindset is zero trust as a concept. Literally, that is what zero trust is. How this gets applied to all of this is just more security, more meticulousness, right? More strict versus accessible. Because a phrase that I'll very frequently say in any of these InfoSec classes is accessibility is the antithesis of security. The more convenient and accessible something is, the less secure that it is. When we're talking about the internet, it's always going to be preferred to make things as strict and stringent as possible because there are a lot of bad people just waiting for the opportunity to arise on the internet. So greater security, stronger access controls, and improved monitoring capabilities is going to be a big thing. Right? So expanding upon decentralized networks, there's a lot of concepts that are examples of it, like blockchain technology, peer-to-peer networks, which are, as opposed to relying on centralized network administrative devices like switches, routers, and admin servers, each device governs itself. And this is more of a collaborative relationship devices have with each other. So it's a quote unquote network, but each device gets essentially to say their own thing and have their own say. They're essentially self governed devices that all contribute to some larger process, more or less. There's a lot of examples of this, like Bitcoins and cryptocurrencies are based on this. Shared processing environments, grids are based off of this, a lot of different things. But the idea is that, yeah, as opposed to centrally managed, these are devices that are self-managing that are more collaborative in nature. Right? Decentralized because by nature, peer-to-peer networks are never in a single building. Like this may be my device on the East Coast communicating with a device on the West Coast, which is also communicating with a device on every major hemisphere on the planet. So we're considered a peer-to-peer because we're kind of a network, because we're functioning like a communicating network, but not with the same kind of centralized infrastructure like a traditional network would have. Right? A very prevalent nowadays, especially related to cloud, is content delivery networks, which I have a very simplified diagram down on the bottom. Content delivery networks are, you can kind of summarize it with a rhetorical question. Imagine the distribution and size of AWS, Amazon Web Services, or just Amazon as a network, right? These are networks that have what's called an origin server, like the primary server headquarters of Amazon, but they have smaller data centers and servers distributed all over the planet closer to their primary service areas, right? Name a large distribution of customers, they have a data center, a collection of servers close to that customer area, that region, to better service them more locally. Because again, if nothing else, physical proximity is a direct effect on performance reliability and performance of these services, of all services. So that's a big focus on content delivery networks and what they do, right? Regional distribution, that is essentially large as possible scale network segmentation to facilitate vast geographical distributions, like, not just East Coast, West Coast, Mountain, and Central, but United States, South America, Asia, so forth and so on. Very large scale, physically distributed networks. This is where you start seeing the term region coming in, where it's again just network segmentation that accounts for a phrase that actually encompasses a lot of this, the economics of scale. How do a lot of these basic concepts change when you're not just talking about an enterprise where it's 100 computers, but hundreds of thousands of computers across the globe. Large distances as well affect how a lot of these things end up getting implemented. So, virtualization. If there's a technology that generally is why modern day cloud can exist at the scale and scope that it does, it's virtualization. Primarily, a type of virtualization called containers. So, looking at the diagram that we got here, a traditional virtual machine has an operating system in it, right? When you think of accessing a VM, you're accessing a virtual desktop environment that thinks it's a physical machine. It's just a virtualized one. Something called a container does not have an operating system, and that is what the difference is. Operating systems take up a lot of resources, a lot of processing power, a lot of hard drive space, a lot of RAM. They take up a lot of processing power, a lot of computational resources. With containers doing entirely away with what's called the guest operating system, you can effectively fit many more containers on the same hardware as a traditional virtual machine would. Assume the left and the right same hardware specs, same hardware specifications, but notice how many more how many more containers you can fit on there. This is much more efficient than using a traditional virtual machine. What you're looking at in terms of this container platform here, something called Docker, is a very well-known one, is what the modern day application server looks like. Because again, think of Gmail being a constantly good example, right? How many users does Gmail have to service at any one time? Some insane number. So how many running virtual machines would need to run to have Google be able to service that many people? It would be some insane number. And it is. It's some insane number. Gmail could do this by using traditional virtual machines, but the amount of physical servers they would have to deploy would be insane. They'd probably be able to afford it. They're Google, but it's vastly inefficient given an alternative. You can cut the number of servers down by one half or more by essentially just using containers. Because if you think about it, all you're doing with Gmail is remotely accessing an application that's being run and processed somewhere else. When you use Gmail, you don't access a Google desktop that's made just for you. You're remotely streaming that application into your browser, application streaming. So because there's no OS actually involved, why have one? So I can fit many more what are called instances of Gmail on one server to service many more users from one place. Multi-tenancy is enforced here much better. You can run applications with traditional virtualization. The left is valid. It's just a matter of efficiency, right? What it comes down to. Again, scope and scale. A lot of other concepts that contribute to this is VPC. At least from CompTIA's perspective and functionally, the term VPC is very similar to how you would refer to a VPN, but when connecting to cloud resources and cloud servers. What is the main difference here is that where VPNs are just a direct point A to point B connection that you define across the internet or across networks, VPCs are similar, point A to point B, direct connection to a virtualized network. Because again, going back to this content delivery network concept, this is an entire network. Acts as an entire infrastructure. So when you're connecting, quote unquote, to Amazon, you're connecting to this large, physically distributed, intensely large thing, but it has one single network identity. This is all virtualized. There's no way to have something like this act as one entity unless you virtualize them, virtualize it a lot, and it is, right? In order to exist at the size they can efficiently, it has to be heavily virtualized. So that's why you have a virtual private cloud you're connecting to, right? Serverless computing. In its most basic terms, serverless computing is, for the customer side of things, having the functionality of a server without having a server itself that you actually manage. So for example, I want to be able to send emails. Traditionally, that would require an email server. However, Gmail lets me use that using my browser. That's literally serverless computing. It is one of the most at face level terms that has been coined in the scope of all of this, but at its base, that's what it means. It does evolve a bit into other more complex concepts like infrastructure as code, which we'll see in a second. Otherwise, microservices. So microservices can be defined a couple of different ways, some very complex, but there's a very easy way to generalize it. So think of microservices as different programs, processes, if you will, that are relatively independent, if not entirely independent. This is a feature we often call decoupled. Decoupled. What that means is that these services in isolation can do their job. Some of them are entirely self-contained and can just do their job on their own. But these microservices are also designed to work with each other, collaborate and coordinate to perform much more complex functions and services together, right? This has a lot of different advantages, but gives incredibly high degrees of flexibility for what kinds of complex tasks they can perform, and is baseline necessary to deal with the high amount of complexity and flexibility that modern day cloud services require, amongst other things. It does also mean that if you lose certain services because of outages, slowdown, or whatever, it doesn't make the entire system collapse because you're missing some component because of how decoupled they are. Another baseline or at least foundational technology that's necessary to support all this is called software-defined networking. Software-defined networking can be thought of pretty literally. That really gets you the most of what you need, but it is traditional networking concepts that are now able to be replicated entirely using software and remote access. Like for example, right, normally when I want to set up how your network connects from point A to point B, I would need to connect to my switch, issue commands directly to my switch, or physically change the infrastructure of my cables in order to establish certain connections. But now we have things like VPNs. Instead of relying on directly how the physical network is laid out, I can virtually define routes that update how the network behaves using software and management platforms. So literally software-defined networking concepts allows things like remote access, VPNs, and literally VLANs, virtual LANs, are a software-defined networking concept. Now, if you're taking the Sec Plus, this would be more of the technical the more the specifics that you would be grilled on the test, but it also outlines just what are considered the different aspects of SDN that make it what it is. So SDN is also frequently defined by what are called the planes. These are different components of an SDN technology that handle the aspects of a network that are necessary to do what it does. The control plane, for example, is what defines the rules. It sets up policies. It says this is how things should happen. When data A comes from point B, this is what goes. Essentially sets up those rules. The data plane is what actually handles how the traffic gets forwarded and switched. So the data plane is the closest to what switches and routers traditionally do and proxies traditionally do. What is actually handling the data based on the rules that are handed from the control plane, and the management plane is monitoring. Very frequently in my classes, I'll misname this intentionally and call it the monitoring plane because that is explicitly what it does. So statistics, auditing, metrics, things of that nature, which are incredibly important given that, again, these kinds of concepts are applied and necessary for these kinds of infrastructures, widely distributed, otherwise very difficult to monitor and maintain. So having solutions geared specifically towards good managed centralized management is key here. Management of virtualized components, key. What else we got? So considerations for cloud infrastructure security is essentially all of the main things that we've been talking about, but applying scale and large scale distribution. Because when it comes down to it, cloud services still use things like firewalls, still use things like proxies, still use things like, IDPSs. However, a lot of these devices are placement based, right? How do we have an IPS that can meaningfully inspect and protect something as widely distributed as a content delivery network? Heavy use of proxies is a short answer, right? All traffic that you're sending to and from a cloud provider is going through a proxy. These proxies dictate where this traffic then gets redirected to. By having the cloud provider having all of your traffic go through a dedicated proxy, that proxy can then forward everything through a choke point where the security devices are going to be placed. Because Amazon and Google have customers literally all over the world. The only way they can centralize, quote unquote, how traffic goes through their security systems is by first having it go through a proxy, which redirects as they need, right? Cloud providers' proxies are devices referred to as CASBs, and they are literally designed for this purpose. And because of the fact that they would be handling such large amounts and variety of traffic, these devices are incredibly advanced. They are called cloud access security brokers, is their full legal name. as I like to call it. But yeah, by definition, these are advanced proxies that can handle all sorts of traffic in high volumes. And the proxies themselves tend to also have the security controls that we need and we want, because cloud providers are aware that it would otherwise be impossible to manage this widely distributed amount and types and varieties of traffic to their infrastructures. It just would be. So they have to centralize things using these gateways, right? SASE is a collection of, literally, the name is pretty self-explanatory, secure access service edge. So essentially, these are cloud-based services or services that are centered around edge services like firewall, what traditional firewalls, proxies, and IPSs do, but for large remote access services like cloud. Both as a service that you can rent as a customer. So if you need a very robust and diverse remote access cloud security solution, this would be that. But also, SASE does effectively describe the ways that cloud service providers manage and forward traffic so that they can meaningfully protect their own infrastructure, again, by use of these proxies and these gateways in order to actually control where traffic goes. And this last little mini section is a quick blurb on specialized systems, which, well, we could just talk about the two things it does. The main thing that it does talk about, and that is embedded systems, and a small little here and there about smart devices. So an embedded system is, if you actually remember the way that I've described microservices, that is essentially the same definition. But where a microservice is, a collection of programs and processes like software that are decoupled but work together. Instead of software, expand it to devices, something a little bit more big. So outside of software, devices, right? So I have a bunch of different devices that are in and of themselves self-functioning, sometimes, if not entirely, self-contained. And these devices, when working together, can coordinate and become something much more complex, so forth and so on. So you have a lot of different things that this could be because it's not defined by functionality. So on our medium scale example, smart home automation, your Alexa and your smart thermostat, entirely self-functioning. They don't need one another to work, but they become a smart home when they coordinate and they work together to enable more advanced tasks and automation. Your smart home is an embedded system in medium scale. Smallest scale would actually be your smartphone because of all the diverse technologies in there, but that's a conversation for somewhere else. Largest scale examples, we have industrial control systems, the type of centralized infrastructure that coordinate and control large scale, complicated, critical infrastructure like manufacturing, like waste processing, so forth, so on. Right? A term that's frequently associated with these specialized systems, and by definition, these are all specialized because each component is its own self-contained or unique thing that's self-functioning. You can mix and match any component that kind of has these specifications to make whatever kind of embedded system collection you want. So specialized. Real-time operating systems are highly customized and specialized OSs that are designed around high speed and high redundancy. The kinds of places you see this is elevator control systems, traffic control systems, and airplanes. Because if there's a place you don't want an OS to randomly have a blue screen, it's probably an airplane. So highly customized because the types of components within those systems are usually very specialized. Like the operating system of a plane needs to be very aware of plane instrumentation and measurement, so it has to be uniquely tailored to it. Traffic control systems and again, elevator control systems, speed and responsiveness for obvious reasons, absolutely. So again, on your largest scale example, you have ICS's industrial control systems, which is what we've done to blend old scale, what we call old school operational technology, the actual manufacturing equipment, the old infrastructure that did already exist, with modern day networking concepts to allow for remote control, access, and monitoring, drastically cutting down on things like, physical injury and things of that nature, but also allowing for these largely physically distributed networks to be managed in a way that's sensible because some of them span many, many different state boundaries. SCADA referring to the actual control part of the industrial control system. This would be the platform that somebody's working at to actually monitor and manage these things. That then makes us get into Internet of Things, smart devices, IoT, the fancy technical name for smart devices. These are, end quote, Otherwise mundane objects that are given some kind of network connectivity. Because like embedded systems, what specifically follows that designation is whatever the hell somebody decides to put an IP address in. And frankly, most IoT devices are what make up embedded systems, right? Because that's what smart home automation is. Your Alexa is a smart device. Your smart thermostat is literally a smart device. Smart devices working in conjunction make up an embedded system. Most embedded systems are a collection of smart devices, if not most of them are. So, generally, when it comes to the security vulnerabilities, concepts, and concerns with smart devices, they are the exact same ones that we see as the concerns for industrial systems as well, because they are foundationally the same. So, the idea with smart devices and these self-contained but often miniaturized components that can make up this larger system, a couple of key design elements are low power consumption. Low power consumption means you can't do a lot of high processing needs things like good encryption or certain strong security implementations. Accessibility and communication are at the forefront of their design because they have to be very good at communicating with each other and other wireless devices like your phone. Anytime you have something that's more accessible, it's less secure. And a lack of standards. A lot of these are very new, not standardized and specialized. You know what a very bad, you know what a common issue with something that's highly specialized is? You cannot apply standardized security to it easily. Sometimes, but not easily. So normal security things that would work elsewhere might not work here very well because of the specialized nature of them. That extends to, again, small to large scale industrial control systems because they're all made up these diverse components. And this circles back all the way to what we were talking about with attack vectors is not only do you have each of these things that are each unique, but each of their unique vectors of vulnerabilities contribute to the larger whole, making security a nightmare to try and account for all things that are happening here. And lastly, what I'll leave you off with, the very last thing in the last slide, is what some people call a case study, but just a good example that highlights the results of these devices being less secure by design, not even by intent or oversight, but by design, is a famous malware called the Mirai malware. What this thing did is that it infected smart devices, usually like cameras or really anything that had internet access, and it was self-replicating, like a worm type virus. So it would infect a smart device, look on the local area for other smart devices because they rarely exist on their own, because embedded systems often come as a collection of devices. So it would infect one, scan for others, and infect them too and replicate. It would then continue this process, and it was used to create one of the largest, if not the largest, botnet generally in history because it just kept finding these smart devices. The basis of it, one, smart devices are designed to be very good at communicating with each other pretty easily. The other part of it was one of the oldest age-oldest human problems with security, and that is people do not like to change default passwords and usernames. Because these devices were new and they had no standards to them, the default usernames and passwords were things you would expect, admin, and the password was password or admin. So the Mirai just kept being able to infect things because one, no one can reliably change their default passwords because people just don't. It's inconvenient. Most people won't. And then two, it took advantage of the fact that it really just took advantage of what these devices were designed to do and being able to communicate well with each other. So it was the human-based issue combined with the inherent lack of, not even lack of, the inherent less security that the design specs contributed, and it just became what it was. So yeah, it's both a criticism of just being mindful of the types of technology you're using and what they are designed to be, combined with basic level human training and awareness for something as simple as changing a default password, because it can make a malware just go like wildfire and become a real problem real quickly with little to no effort. So that ends up being the last thing I got. And that's like 1 minute, 1 minute over the 2 hours. So that is this. Just, I mean, it's closing notes. If you gotta go, you gotta go and all that. And I thank you for your time and your patience, but just a quick little, here and there. So yeah, like I was saying during the beginning, this is more than anything, this was a snapshot of the Sec Plus certification, the whole certification exam. A lot of these concepts, you'd be going over a little bit more in depth definitely with, if you're taking the certification exam to take the certification, we'd be focusing a lot more on, this is what the test wants from you, this is what the test needs of you, contextualizing with more examples like that Mirai malware being a good example of, highlighting botnets, weaknesses, and things of that nature. Yeah, and things of that nature. That's really it. Um, Expanding to specific topics a bit more, like different kinds of malware, categories of vulnerabilities, and contextualizing the best use cases for a lot of these security concepts to the actual kinds of attacks that they would mitigate. Like, how does ARP poisoning actually affect a switch, and what does that mean, and what are the actual mitigation strategies we can use against those? Like, where does port security actually stop attacks like ARP poisoning and man-in-the-middle attacks? That's where you start. That's how the Sec Plus expands from these basic architectural concepts that we've been hitting. Essentially practically applying security to things that they would actually stop. But yeah, just as a preview, how do we get the CPE certification for this? Good, fair. What I imagine a lot of people are here for. So that whatever email you signed up with, they should start sending those out automatically. But it is a busy week, so it might take a little bit. If you need to execute those, expedite your continuing education credits, then you will want to email helpdesk@trainingcamp.com. I'm typing it in just so you also have that. Helpdesk@trainingcamp.com. Ask them for your certificate of completion, quote unquote, or just say certificate. They'll figure it out and they'll send it to whatever email you registered with. Hopefully sooner rather than later. Like I said, it's a busy week, so that's the best way to expedite it right now. Good stuff. So yeah, otherwise, again, we're past those 2 hours. So if you got other places you'd rather be or places you need to be, then you're good. Like I said, I thank you for your time and all that good stuff and your attention. If there's anything else you need from me, I'll stay here for at least another minute and all that stuff. But otherwise, yeah, maybe I'll see you in maybe I'll see you in one of the full classes. If so, I'll be glad to have you. Otherwise, you have a good night and all that good stuff, and enjoy your weekend.